morning. I am Renu Sharma, Assistant Professor, EC Department. Today I am going to start with the second unit of the subject, that is Communication Engineering. And today's lecture, the very first topic of Unit 2 is related to angle modulation. Now, angle modulation, we will discuss its introduction, then concept of angle modulation, its basic definition, and there are two types of modulation that is related to angle modulation. First one is phase, then frequency modulation. Then we will discuss the frequency deviation that is related to frequency modulation, relationship between FM and PM, and then single tone FM. Now, first we will begin with what is angle modulation. So, there are two components which exist in the signal, that is related to the total phase angle, that is only the phase and the frequency. So, the phase and frequency of the message signal is varied according to the message signal. The amplitude is kept constant. So, let us take an example of a signal such that ST is equals to A cos omega CT plus phi t. Now, if you look into this equation, there are basically three parameters. First one is the amplitude, this is the frequency, that is carrier frequency, and this one is the phase angle at time instant t. So, in case of phase modulation, we have to change either the frequency of the signal or the phase of the signal according to the proportional to the amplitude of the message signal, and this particular parameter has to be kept constant. So, if I consider this as a phi t whole, so this will be known as total phase angle, which is equals to phi t. You can also write it as phi naught, which means at time t equals to 0. So, this will be the equation for from which you can see that how the angle modulation will in that particular angle modulation, how the phase and frequency of the signal will be changed. So, this is the concept of angle modulation. In this, the total phase angle of the carrier is varied according to the instantaneous value of the modulating signal or the message signal, keeping the amplitude constant. So, you can see over here that consider again the general carrier. So, this is nothing, this is the carrier signal, which is Vc cos omega Ct plus phi c. Now, phi c is nothing, this is the phase that we have to vary in case of phase modulation. Omega c is the carrier frequency that we have to change according to the amplitude of message signal, and Vc is the only the amplitude of carrier signal which has to be kept constant in case of angle modulation. So, this represent, that is omega Ct plus phi c, represents the angle of the carrier or the total phase angle. So, there are two ways of varying this, either we can change the omega c or phi c. So, next is what are the applications of this angle modulation. Like, first application is radio broadcasting. Radio broadcasting basically means when we are broadcasting the signal in radio frequency range, like in the megahertz range, the FM radio that you are listening. So, that is related to this radio broadcasting only. Then, second application is two-way mobile radio, which means that full duplex communication in case of mobile communication, that is also related to this AM, FM, PM concept, that is angle modulation. Next one is microwave communication, which means that when the communication is in the range of 1 gigahertz or greater than 1 gigahertz, then there will be microwave communication. Next one is TV sound transmission. So, in this case TV sound transmission, we are using vestigial sideband. So, that is also a vestigial sideband, that is also a kind of modulation that we have already learnt in unit first, whose bandwidth lies between DSP, SC and SSP. Now, next one is the cellular radio, where it is related to the cell phones. Next one is the satellite communication. So, in this case the communication is done using satellite. So, next one is advantages and disadvantages. So, advantage of this angle modulation is, first one is the noise reduction, second is improved system fidelity, then more efficient use of power. So in this case, in case of AM or FM, since we are not transmitting the extra information, we are just transmitting the side bands. Let us take an example of narrowband FM or wideband FM. In case of narrowband FM, only 2 sidebands are transmitted, but whereas in case of wideband FM, infinite number of sidebands are transmitted depending on the formula of J and beta, that is known as Bessel function. So depending on this, depending on the value of n, if n vary from minus infinity to infinity, which means, or you can say 0 to infinity, which means that there are infinite number of sidebands are there in case of wideband FM. Which means that more number of users can use this particular type of modulation technique. Next one is the disadvantage. Disadvantage is increased bandwidth and use of more complex circuits, because we are changing the phase and frequency of a particular signal. So more complex circuits are required because we are not dealing with the amplitude. Changing of amplitude is much simpler as compared to the changing in phase or frequency of a signal. Now next one is frequency modulation. So in FM, the message signal MT controls the frequency FC of the carrier. So consider the carrier signal, this one, then the FM wave may be written as. So here we are basically deriving a standard equation for the frequency modulation. So the FM signal can be written as VST is equals to VC cos omega C plus frequency deviation. Of frequency deviation is denoted by delta F, or it can be written as delta omega, where the frequency deviation is dependent on MT. So given that the carrier frequency will change, we may write for an instantaneous equation, that is VC cos omega it is equals to VC cos omega it, which is equals to VC cos phi I. So where phi I is the instantaneous angle, which is denoted by omega it, 2 pi is equals to 2 pi FIT, and Fi is nothing, it is the instantaneous frequency of the input signal. Now next, in continuation, since phi I is equals to 2 pi FIT, so we can also derive an expression for omega I or Fi, which is just the differentiation of the instantaneous phase angle. So frequency is proportional to the rate of change of angle. So this can be drawn from this particular equation. So Fi is required in case of FM, and phi I is required to be calculated in case of PM. In case of phase modulation, we have to calculate the instantaneous phase angle. If Fc is the unmodulated carrier and Fm is the modulating frequency, then we may reduce this particular equation to Fi is equals to Fc plus delta Fc cos omega mt, which is equals to 1 upon 2 pi d phi I by dt. So delta Fc is nothing, it is the peak deviation of the carrier signal. So hence we have to we can write this equation as 1 upon 2 pi d phi I by dt, which is equivalent to Fc plus delta Fc cos omega mt, and this can also be written as this particular equation, that is d phi I by dt is equals to 2 pi Fc plus 2 pi delta Fc cos omega mt. So that is related to the frequency modulation. Now next, after integrating this particular equation, we can write it as omega c, integral of omega c plus 2 pi delta Fc cos omega mt, and phi I will be is equals to this particular equation. Means after integrating, we are when we are going to integrate cosine, then we will get the sine function, and omega c after integration it will be omega ct. So if you are going to see this equation, so this will be the standard form of FM, that is VST is equals to VC cos, in bracket it will be omega ct plus delta Fc upon FM sin omega mt. Now this can be written as beta f. What is beta f? Beta f is nothing, it is the modulation index for the FM signal, that is delta Fc upon FM, or you can also write in terms of omega, delta omega upon omega m. So this is nothing, this is the modulation index for the FM signal. Now next, from here from the standard equation that I have told you, modulation index parameter is considered. So the ratio of delta Fc upon Fm is called as the modulation index, that is denoted by beta. You can also write it as beta F also. So that means it is peak frequency deviation divided by modulating frequency. So note Fm as implicit in the above equation for VST is a nonlinear process, that is the principle of superposition does not apply. So the FM signal for a message signal MT as a band of signals is very complex, hence MT is usually considered as a single tone modulating signal. So when after deriving this particular equation for the FM, this particular equation where we can replace this by beta, now we have to put the value of, we have to consider the value of message signal. Since we are considering the case of single tone modulation, then this will be the corresponding message signal where there is only one frequency component present in the message signal. So MT will be is equals to Vm cos omega MT. Now if we consider it as multiple tone, then this will be Vm1 cos omega M1t plus Vm2 cos omega M2t and so on. So if there are 3 frequency components, 4 frequency components, that is of totally your choice. So there are 2 frequency components are present over here. So this will be a multiple tone modulation if we consider our message signal in this form, and if we consider our message signal in this form, then there will be only one frequency component, that is single tone modulating signal. Now if we are going to put this particular equation, then the equation which is standard one, it can be expressed in terms of Bessel function. So VST can also be written as Vc summation n is from minus infinity to infinity Jn beta. Now this is the Bessel function of first kind having parameter beta, and it is of nth order, cos omega c plus n omega m into t. Now we can put various values of n, that is from minus infinity to infinity, but here we are considering from 0 to infinity, like you can see over here, where Jn beta is the Bessel function of first kind. After expanding this particular equation for few terms, you can see that Vc J naught beta, this is an amplitude at frequency omega c, then Vc J1 beta at frequency Fc plus Fm, this is the second term. So this is how you can reduce this, expand this particular equation into following terms. Now you can put the various values of J naught beta. So after considering this expanded version of the equation, you can also use the properties of Bessel function, like for the even value of n, for odd value of n, there are several properties that exist, and you can further reduce this equation, simplify this equation. So this is the, now this will be the FM frequency spectrum. Now there is one important thing that you have to consider, the value of beta f. Now beta f is nothing, it is the modulation index. Its value can be greater than 1, or beta f, it can be less than 1. So in this case it is known as WBFM, that is wideband FM, and in this case it is known as narrow band FM signal, that is known as NBFM. So this is the important condition that you have to consider while solving any kind of numerical. Let us take an example that you have to calculate the value of beta using the formula delta f upon omega m, and then you have secured some value, let's say 2.3, then 2.3 means that beta is greater than 1, so it will be considered as a wideband FM case. So there are infinite number of bandwidths exist in this particular case. So this is the representation, frequency representation. Now you can see that this is at n is equals to -4. So n is from -4 to +4. We have we have drawn this particular waveform from -4 to 4, then the amplitudes drawn are completely arbitrary, since we have not found any value for G and beta. So this sketch is only used to illustrate the spectrum. Now next is the phase modulation. So the phase angle phi is varied in accordance with the baseband or the modulating signal. The mathematical representation of this particular will be same as shown. So knowing that the unmodulated carrier signal is expressed by this particular equation, so this will be the carrier signal considering the frequency and the angle, and phi is nothing, this is the total phase angle. So we have to vary this total phase angle, and we have to derive an expression for phi I, that is instantaneous phase angle. So neglecting this theta naught, this phi can be written as omega ct. So according to the phase modulation, this phase angle phi will be varied linearly with the baseband signal, that is xt. So let the instantaneous value of the phase angle be detected by phi I. So in case of FM, we have to calculate fi. In case of phase modulation, we have to consider phi I, that is the instantaneous phase angle. So let this phase angle be written as omega ct plus kp into xt. Now kp is another parameter that is known as proportionality constant, and its value is known as, it is known as phase sensitivity, and its unit will be radians per volt. Whereas in case of FM, there is a parameter that is kf, and its unit will be hertz per volt. So kf will be can be written as hertz per volt. Since the expression for the unmodulated carrier wave can be written as Ct is equals to A cos phi. Now next is, therefore the expression for the phase modulated wave will be St is equals to A cos phi I. So substituting the value of phi I over here, it can be written as St is equals to A cos omega Ct plus Kp into Xt. So this is the required mathematical expression for the phase modulated wave. This is the standard equation for PM. Now next one is the frequency modulation. So in case of this frequency modulation, what is frequency modulation basically? When we are seeing this FM, in case of FM, we have to change the carrier frequency omega c depending on the amplitude of message signal. Let us take an example, like this is your message signal xt, and this is t. This is your carrier signal. So let us take an example where we are going to see that what is frequency deviation. So this is a message signal. This is a message signal, and this is your carrier signal having frequency omega c. So this will be the center frequency. So we have to change the frequency of this signal proportional to the amplitude of this signal. Now you can see in this time duration the amplitude is maximum, and in this time duration the amplitude is minimum. So we have to increase the frequency here, and we have to reduce the, so minimum frequency will be here and maximum frequency will be here, and from the center frequency, that is omega c. So that is what it is shown over here. This is omega c, center frequency. This will be the maximum frequency, that can be written as f max corresponding to this one, and this will be the minimum frequency, that is known as the negative frequency, most negative frequency. So if you are going to calculate this value, this is known as positive deviation, this is known as negative deviation depending on the amplitude of the message signal. So its value will be fc plus delta omega or delta f, and f minimum will be equals to fc minus delta f. So you can see that this is known as a frequency deviation. Its formula will be modulus of kf, that is frequency sensitivity, its unit is hertz per volt, multiplied by the maximum amplitude of the message signal. Now why we are considering it maximum? In case of single tone, it is quite easy to calculate the value of maximum, calculate the amplitude of the message signal. But when we are dealing with the multiple tone signal, there are multiple frequency components are present and multiple amplitudes are there. So, we have to consider only the maximum amplitude. So, this formula will be kf into xt max. Now, next we are going to derive an expression and draw a block diagram to see the relation between FM and PM. So, this is the expression for PM wave, that is ST is equals to A cos omega CT plus KP into XT, and this is the standard equation for FM wave, that is ST is equals to A cos omega CT plus KF integral 0 to T XT dt. Now, KF is nothing, it is the frequency sensitivity, its integral is 0 to T XT dt. So, that is how we have to reduce a relationship between this FM and PM. So, as you can see from this standard equation, that in case of FM here integral is used, and in case of PM there is no integral which is used over here. So, in case of this FM using PM, an integral has to be used at the input side through which this particular signal will be passed. So, here we are getting this integral xt into dt. So, this will be passed through a phase modulator. At the output of the phase modulator there will be an FM signal, and at the input of this there will be a carrier signal, that is A cos omega CT. So, this is how, if we are having phase modulator and we have to derive an expression for the FM signal. So, this is the block diagram that we have to use. Next one is the PM case. So, and we are having frequency modulator. So, in case of frequency modulator, first XT signal is to be passed through a differentiator dxt by dt, and from this differentiator it has to be passed through this frequency modulator. To the input of this frequency modulator there will be a carrier signal, and then a PM signal will be generated at its output. So, this is how we can draw FM using PM and PM using FM. Now, next one is the CARSON'S rule for bandwidth calculation. So, that is the very important formula for calculating the bandwidth. Its formula will be twice of delta FC plus FM. Now, FC is the frequency deviation that we have seen. Its formula is FC, delta FC upon FM can be written as beta F, that is the modulation index. So, we can also write this formula as 2 beta F plus 1 into FM. So, this formula can also be reduced to this particular formula. So, that will be the CARSON'S rule for bandwidth calculation. Now, next is generation of FM. So, the FM signal will be generated using two types. First one is voltage to frequency converter, next one is voltage controlled oscillator. In case of voltage to frequency converter VCO or the voltage to frequency converter, the output frequency is dependent on the input voltage amplitude. So, that is what we are doing, we are changing the frequency of the carrier signal proportional to the amplitude of the message signal. Now, next is two types of FM are there. First one is narrow band FM, next one is wide band FM. In this case, we have considered one, it can also be standard form. In the standard form, it is considered as 0.3. When beta is less than is equals to 0.3, then it will be NBFM. When beta is greater than 0.3, then it will be wide band FM case. So, this is in this case there are only two sidebands are there, that is upper band, upper sideband, lower sideband. In this case there are infinite number of sidebands exist. So, in today's lecture we have discussed about introduction of FM and PM. Thank you.